Now moving ahead, let's look at something called spanning set. So what are spanning sets? A set of vectors x1, x2, xk is said to, let's call it, span a vector space S if any vector x belongs to S can be represented as a linear combination of x1, x2, xk. What is a linear combination? So what does this mean? Is so any vector x, if it can be written as a linear combination, that is alpha 1 x1, this is real number, plus alpha 2 x2, alpha n, alpha k xk. If I can write all the vectors in S like this with some numbers alpha 1, alpha 2, alpha k, for some if I belongs to R, then the term is all. Then this is called, these sets are called to span, are called spanning vectors of S, of the space S. So for example, let's say we have n is equal to 1 0, a2 is equal to 1 1, a3 equal to 0 1, a4 is equal to minus 1 0, a5 is equal to 1 minus 1. So actually they span ourselves. We'll see how. We'll see through the diagram. So A1 is 1 0. This is A1. This is A2. 1, 1. This is A3. A4 is, let's use some other. This is A4. And I think this is A5. So these are the vectors. Turns out any vector in R square, you can write as a combination of these vectors. For example, let's try to write 2, 1. So it turns out you can write it as A1 plus A2. A1 plus A2. And so where alpha 1 is 1, alpha 2 is 1, alpha 3, alpha 4, and alpha 5 are 0. It turns out these alphas need not be unique. So you can also write it in some other way. So you can also write 2, 1 to be A1 plus A3 minus A4. This also actually is 2 1. So it will be 1 0, 0 1 minus minus 1 bn. This gives me 2 comma 1. So this set of alphas need not be unique, but you can write in some way uh, all the vectors of S in some way. So a natural question that arises is uh, what are the minimum number of vectors uh, required so that their linear combination spans S. So this is one natural question that arises. Why this arises is like if you see here, you may not require. So if I tell you that all the, so we have A1, A2, A3, A4, A5, but A1, A2, and A3 are also sufficient to span all the vectors. So any vector in R square you can write using A1, A2, A3 also. It turns out you can also write any vector using only A1 and A3, any vector. So what is the minimum number that is required for spanning all the vectors, for representing all the vectors as a linear combination of any given set of vectors? What is that minimum number required? So for trying to answer this question, we have to define one more term called linear independence. So what is linear independence? Yeah. So a set of vectors x1 comma x2 comma xk is said be linearly independent if alpha 1 x1 plus alpha 2 x2 alpha k xk equal to 0. If the solution to this equation implies alpha I equal to 0 for all I. That is alpha 1, alpha 2, alpha k are all 0. So this is the definition of linear independence. So what does this mean is like if a set of vectors x1, x2, and xk, if we say that some linear combination is 0, then that can only happen if their respective coefficients are 0. So they should not add up to 0 for some non-zero real number or non-zero coefficients. So the linear combination is 0 implies individual coefficients are 0. So why is this important? So let's say if if alpha 1 x1 plus alpha 2 x2 alpha k xk not equal to 0, if they are not 0, then the vectors are called linearly dependent. called linearly dependent. Uh, Sorry, equal to 0 for some non-zero alpha i's, then they are called linearly dependent. What does this mean is, and one of the vectors can be represented as a sum, as a linear combination of others. So, so let's take an example. The similar example, but less number of vectors. A1 is equal to 1, 0. A2 is equal to 1, 1. A3 is equal to 0, 1. So this is A3, this is A1, this is A2. So are these linearly dependent or independent? So let's see. So let's say alpha 1 A1 plus alpha 2 A2 alpha 3 A3 equal to 0. Does this necessarily say that alpha 1, alpha 2, alpha 3 are 0? It turns out that it's not. So if alpha 1 equal to 1, alpha 2 equal to minus 1, and alpha 3 equal to 1, then also this turns out to be 0. So A1 minus A2 plus A3 equals 0. And it turns out this tells us that A1 can be written as a linear combination of other two, that is A2 minus A3. A2 can be written as a linear combination of others, A1 plus A3. And A3 can also be written as A1, A minus A1 plus A2. So this is what, if they are linearly dependent, one of them can be written as a linear combination of the others. Now let's take only two vectors, A1, A2. Are these linearly independent or dependent? So let's see, alpha 1 A1 plus alpha 2 A2 equals 0. Is there a way uh, where alpha 1 and alpha 2 are not 0, but still this is 0? Actually, it's not possible. So you can say that alpha 1 0 plus 0 alpha 2 equals 0, which means alpha 1 equals to 0 and alpha 2 equals 0. So this means that these are linearly independent, and it also turns out that you can say that A2 cannot be written as a linear combination of A3, or like A2 cannot be written in terms of A1 only. You can't write it. So these are this is what, and now I'll try to explain why this helps us in, like, why this helps us in answering this question. What are the minimum number of vectors required so that their linear combination spans S? So the answer is, for the minimum number to span S, those set of vectors should be linearly independent. Why so? because if they're not, because the other vectors, let's say we had a1, a2, a3, a4, a5, and we want to span r square. So the minimum number required uh, it can be thought of that those vectors should be linearly independent. Uh, why so? So let's say they are not dependent. So they are not independent. That is, they are linearly dependent. Then A3 can be written as a linear combination of the others. So if they are dependent, all the extra vectors can be written as a linear combination of the only linearly independent vectors. And in the end, we are only left with the linearly independent vectors. So the minimum number of vectors required to span R square can be looked upon that those number of vectors should be linearly independent. Should be looked at a minimum number of vectors required for the set to be linearly independent. They both are the same. Now moving ahead, we'll define what are bases, which is a combination of these two. What are basis vectors? So a set of vectors said to be a basis vector space S if it is linearly independent and spans S. What does this mean? Spans means those set of vectors should their linear combination should represent any vector in S, and linearly independent means uh, among those vectors, none of the vectors should be able to represent it by a linear combination of the others. If this is true, this is the minimum number of vectors that is uh, required for representing any vector in spaces. Okay. Uh, that is, so basically the number of vectors in a basis is actually the minimum number of vectors required to represent any vector in space S. So we'll look at some examples. We'll look at the examples in R square. A1 equal to 1 comma 0. We saw this example earlier. A2 is equal to 1 comma 1. It turns out they are linearly independent. We saw earlier. We also talked about that they can span S. Any vector in S can be represented as a linear combination of A1 and A2, which means that these can be called as bases of R square. We'll see one more example. A1 was equal to 1 comma 0. A2 was minus 1 0. It turns out they are not linearly independent. Why? Uh, A1 minus A2 equal to 0. So 1 and minus 1 alphas, but and their linear combination will lead to 0. They are not linearly independent, and they also can't span S. So that's why they are not a basis. We'll see two more examples in which they are linearly independent but does not span R. So let's say we have A1 equal to 1 comma 0, A2 equal to 1 comma 1, A3 equal to 0 comma 1. So they span us, but not linearly independent. We saw earlier as 1 minus 1 1 plus equal to 0. Now, so this is also not a basis. Okay. Similarly, we can get can find let's say P1 is equal to 1 0 0 and P2 is equal to 1 1 0. They are linearly independent. They do not span R cube, which means they are not basis. So these are the four examples of how to look at basis. It turns out for R square, by these examples, it must be clear that the minimum number of vectors required to span the whole space S is 2. Space R square is 2. And you can also see it for R cube, you get a hint that it should be 3. Now, there are some properties of bases which are really important, and you should have them in mind. I'll first write them down and then explain it to you. So first is a vector space does not have a unique basis. You can have multiple set of vectors that are linearly independent and also span the vector space S. There are no unique set of bases. So for example, let's say for R square, 1 0 and 1 1 are a set of bases. So are 1 0 0 1. These both are a set of bases. So is 1 1 and 1 minus 1. All these three are bases, and there are many more. There are infinitely many number of bases in R square. So it does not have a unique basis. Then if x1, x2, xk is a basis for S, then any x belongs to S can be Directly represented I for any x equal to alpha 1 x1 plus alpha 2 x2 okay xk alpha i's are unique. What does that mean? So so let's say I have a set of vectors which are bases. Then any vector which I represent unit those basic is unique. We saw earlier that if we have a set of vector with span S, alpha may not be unique. We can have others, but if those set of spanning vectors are bases, then alphas become unique. So, uh, so if x1 to xk are uh, let me give you an example. So 1 0 and 1 1 are, let's say, are a basis in R square. So the way you represent 2 1, then alpha will be 1 comma 2 only. Alpha 1, alpha 2. Sorry, yes. 1 comma 1 only. There is no other set of alphas which you can use to represent this vector using these two basis vectors. There is no other alpha set of alphas. So this is unique for a basis. For a spanning vector, let's say I add one more vector here, those become a spanning vector. We can have multiple alphas but for if they are bases, we cannot have multiple alphas. So any two bases of a vector space have the same cardinality. So let me first define what cardinality is, and then I'll explain you this property. So cardinality is the number of vectors in the basis set. That is what it is in the basis set. Uh, so what this property says is, so if we have, let's say, any two bases, as we saw earlier, 1 comma 0 and 1 comma 1. This is one set of basis set, and there is 1 comma 0, 0 comma 1. So cardinality here is number of vectors in the basis set. Here cardinality is 2. Here is also cardinality is 2. So this property says that there can be no basis vector in R square which has cardinality other than 2. They can't have a single vector A, B which spans whole of SA, whole of R square, and there can't be more than two vectors which are all linearly independent as well as span R square. So cardinality for any basis in R square has to be 2, and they are same for all the bases in any vector space. This property says. Also, dimension of vector spaces is equal to cardinality of basis of S. We saw, which is fairly obvious, that if we have R square, its cardinality we saw is 2. So if you see, the cardinality of basis vector is same as the dimension. This is what the property says, and which means dimension uh, dimension of Rn is n, and cardinality of basis vectors of Rn is n. So there are two more properties that you should note. So a basis of vector space S is a it's called maximal independent of vectors which spans S. So we talked about this a little bit earlier. I'll define what maximally independent set is. Let me write one more property. So a basis of vector space S is a also a minimal spanning set vectors which spans S. So this maximal independent set means that it is the maximum number of vectors which can be independent and also span S. So this is what means which we talked about a little bit earlier. This is the maximum number of vectors which can be independent and span S. What does this minimal spanning set means? It means that this is the minimum number of vectors which can span S. So for example, in R square, we saw uh, 1 comma 0 and 1 comma 1 as one of the basis sets. So these are the maximal independent sets. So you cannot have more than two vectors which are linearly independent and also span S. So, and we can also not have less than two. We can also cannot have less than two vectors which span S. So this is actually uh, the, the only number of vectors that can be inside a basis. So that's what this means. With that, we had a discussion on vector space, uh, uh, basis, spanning vectors, linear independence, and basis. We'll now move to something called function, which you already know, I think. So I'll formally define it. A function f from set A to B is a rule that assigns each way a unique element B fx belongs to B, and it can be represented as this is how it's represented, that f is a rule that assigns every element in B to some element in B. That's what it means. So there are some definitions, like A is called the domain of F, B is called the codomain of F, and then there is something called range of F which can be defined as a set of y which belongs to B such so there exists a x such that fx equal to y. So all those elements in B which are related to some element in A form a range. So it may happen that all elements in B may not be attached to some element in A. Uh, so that can happen. But this range of F is a subset of B. So it can also happen that all of the elements in B are attached to all of the some elements in A. So, but it may also not happen. So for its example, I'll give you very basic examples here. I think you already know what a function is, so I'll not go deeper into it. But fx is equal to x square, and then f, you can also write -1 to 1. Uh, um, f is equal to 1 upon, let's say, mod x minus 1, etc. There can be multiple various different uh, examples of function. Now let's define what is a norm. So a norm, so you might have heard about 2 norm, 3 norm. So they are examples of norm. Uh, so we'll formally define what a norm is in this definition. So norm on Rn is a real valued function. What does this mean? So a real valued function means its codomain is R, real number. Notice its codomain cannot be some Rn. It has to be R. Okay. Then only it's a real value. So a norm on Rn is a real valued function defined like this. Which obeys following rules. First rule that it has to follow is mod x has to be always greater than equal to 0 for all x belonging to R. And mod x equal to 0 if and only if x equal to 0. So all the values, all the components of x should be 0, then only mod x or the norm of x should be 0, otherwise it has to be greater than 0. Second property that it has to follow is, let's have a scalar norm of a scalar multiplication of x. It should be equal to the absolute value of that scalar multiply the norm of x for all x belonging to R. Alpha belongs to R, I mean, it's a real number. It should follow this. Also, one more thing is it should follow triangle inequality. So, norm of x plus y should be less than or equal to norm of x plus norm of y for all x comma y belonging to R. So a diagram that is generally associated with this is mod norm of x norm of y. You can see, so based on the triangle inequality, you can see that the norm of the sum should be greater than sum of the should be smaller than or equal to the sum of the norms of individual vectors. So um, you might have, so we'll discuss some examples, and these examples you might know. So before proceeding with the examples, I want to tell any function which obeys these rules can be called a norm. It can be called a norm. So I'm giving you for examples, but norms are not limited to this. Any function which obeys these rules can be called a norm. So first example, which is very common, is L2 norm or Euclidean norm. So here it is represented by norm 2. Here it means x1 square plus x2 square xn square to the power 1 by. So where x1, x2, x3 are components, x is represented by x1, x2, and transpose. So this is 2 norm. We can also define something called L1 norm. This is just the absolute value actually, sum of absolute values of the individual components. That is x1 absolute value, x2 absolute value. So we can also define something called L3 norm, which is x3 is equal to mod x2 plus. So you can see a pattern here, right? This is one of the function. You can define it. You can define it any other way. These are some common norms that I used. L3 norm, which means x p x1 to power p plus x2 power p plus xn power p. You understand this value of absolute value, I think, because it has to be positive. So this is a general p norm. And in this pattern, we can also define something called L infinity norm. So L infinity norm is just you can say you send the limit of p tending to infinity on the LP norm, which means that you'll be left with max of. I mean, if you move these to infinity, the maximum component will be so high that when rest of them can be compared to can be assumed to be zero in front of it, and you'll get what is called absolute value of the maximum component. So this is what L infinity norm is. So these are some examples. So there is a very important result in terms of norms that we'll use in the optimization. So that result I'll state here and then I'll explain it. So if P norm and Q norm are any two norms, in Rn, then there exists positive constants alpha and beta such that alpha times the norm of p norm of x is less than equal to q norm of x is less than equal to beta times the p norm of x. So basically, every norm q is bounded by some multiple of, so every norm of x, so every q norm of x is bounded by some multiple of every p norm of any p norm of x. So this should be true for any x belonging to Rn. So why this result is useful for the optimization? We'll look into that. So this is true. We'll not prove this results, but this is true. So I'll try to give you an intuition why this is true. And if even if you do not get this intuition, we'll later on come back to this when we are go deep into the optimization. But it's good to have an idea of this beforehand so that you can keep on thinking about this. So let's say we are using a particular p norm as a stopping criteria for an optimization algorithm. Say we use a p norm as a stopping criteria for an optimization algo. That is norm of where we are xk minus x star. That is, this is the optimal value. This is our solution, and this is where we are at current in the current. Its p norm should be less than equal to some threshold. If this happens, we stop our algorithm. We stop our algorithm. If it is less than this, we'll stop. So it turns out that this relation, that result we saw earlier, and if we use this, and while using this stopping criteria, our algo converged. We're using p norm. So can we say, so will it converge if we use q norm? Let's instead of this use a q norm. Less than some other threshold related to q. We use this, will it converge to the same point or will it converge at all? It turns out because of the above result, we can say that yes, they'll converge. They converge with q norm also. This is sometimes called, because threshold q can be written in some form of threshold p here. It can be written in some form because of the above result. So sometimes this is called equivalence of norms. What does this say is like if we in an algorithm we prove convergence with one norm, we can prove it for any other norm. So basically whatever norm we use will converge and will converge to the same point. It does not matter actually which norm you are using in your optimization.